Dimmi tu. Okay. Okay, welcome. Just waiting for the people to sit. Okay, welcome. My name is Simone. I work for an American company called Webtide that provides services and support for the Jetty project. Jetty is an open source web server and server container. So in this presentation, I will tell you a little bit of war stories that we had in the work that we do at our company, which is tuning Jetty for performance in order to be a really fast web server, and also the experience that we had with our clients tuning their applications, typically web applications, using Jetty, and trying to get the best performance also for them. So it's going to be like a little bit of introduction, high-level introduction. How do we do these things? And then I will give you a few examples of real stuff that happened to us in working with Jetty on performance. So application performance. So you've written fundamentally your web application, okay? And then the next question comes, okay, it works, but how does it perform? Well, like many questions in our fields, the answer is it depends. It depends, especially because what you need to do is you need to ask the right questions. And especially the important thing in performance is what is your end goal? What is it, the answer that you're looking for, or the problem that you're trying to solve? So for example, typical problem could be capacity planning, meaning how many machines or how much hardware do I need to buy in order to sustain the load that I'm thinking my application needs to sustain. Or a different question could be, I have my system in production, works perfectly fine. Can I sustain a peak load, for example, in special occasions like Black Friday or tax season, or a earthquake happens and I am the CNN website? Do I go down because everybody's going to the CNN to see the results of the earthquake? Or something different. Can I tune my application for having minimal latency, meaning I want my server-side web application to be as fast as possible, okay? And reduce as minimum as possible the response times. Or I don't care because I know that my web application has long processing times. For example, it goes and does batch computing on the database, etc. But what is it that I want to optimize is, for example, lock usages, or allocation usages, or some other resource that I want to minimize and make my application more efficient and consume less resources, so that if I deploy it on the cloud, I spend less money. So in order to do this kind of assessments, I need to be able to do load testing on my application. And typically in our experience, there are two kinds of load testing. One is called steady state. We call it steady state load testing. And the other one is called limit load testing. And they are quite different, even though they're still both load testing things. But the steady state load testing typically runs at what we call the nominal resource usages. The idea is that you run a load test with a load on the system that mimics what you will have in production. And so you want to have in production a machine that typically does not run at 100% CPU. What you want to have in production to be safe is like, okay, I want my systems to be pretty much at half capacity at most, maybe even less than that, okay? Because I still want to be able to sustain a little bit of variations in the load. For example, I want to be able to say, my load has a typical pattern during the day, there is more load, but during the night there is less load, okay, depending on the geographical zone that you are in. And in this particular case, maybe you don't want to allocate too many machines during the day and then deallocate the machines during the night, but you want to say, well, maybe my machines can handle the load. The curve is not that high or too low, and therefore my machines can handle the load, no problems. So this is what we call steady state load testing. The limit load testing, on the other end, what you really want to do in this case is to run your load test until you saturate one of the resources of your system. Typical resource that you want to saturate is the CPU. You want to try to load as much as possible until the server-side machine goes 100% CPU. Or you want to say, okay, maybe I never reach 100% CPU because I am exhausting one of the other resources before. For example, the network. I am exchanging requests and responses, and the size of the request or the responses is so much that basically I am consuming all the network bandwidth well before the CPU goes 100%, okay? Or you can saturate other things that are specific to your application. For example, you have a connection pool to your database, and you can just saturate the connection pool to your database. You cannot do more queries to the database because you just don't have enough connections. Or other things like the heap memory or application caches and so on and so forth, right? You know your application, you want to say, okay, how does it behave? The number that you typically get out of a limit load testing is a cool number. It's a number that you can give to your boss and you can say, hey, we can go 200. But it's kind of a meaningless number typically because you never want to go in production at that particular resource consumption. You never want to go into production where you are 100% CPU or full network bandwidth or completely exhausting your JDBC connection pool, right? So even if you know that number, sometimes it's just useless. It's a comparison maybe between versions of your applications, but typically, as an absolute value, it has very little meaning. So, as I said, both of these styles of load testing are really useful. Typical case of steady state is capacity planning, also scaling strategies. But if we go back to load testing, limit load testing, what is the usefulness of it? As I said, the number that you get out is pretty much not really useful. But what it is really useful for is you want to know, for example, what is the first resource that you are going to exhaust in your limit load testing. And the second thing that it's really very interesting is, okay, after I finish applying the load and I remove the load, does my system still work? Okay, so can I sustain a big peak in time, but then when the peak goes away in the load, can my system work normally? Or does it have some leak or something so that it cannot work well afterwards? So these are really interesting questions that you would like to answer while doing application performance testing. So we're typically using these steps in order to set up a load testing for your application. The first important step is the setup. And this is probably the step that takes the most time out of it. It's really important to set up your load system in general in a very good way. Typically what we do is that we have one server machine, we have a number of what we call loader machines, okay, and these are clients that impose the load on the server machine, and then we typically have separated one additional machine that we call probe. This machine is optional, but we typically use it because we really want to have this information. If I load my system and I want to take some measurement on the clients to try to mimic the case of I have my system working in production, there's a load coming from elsewhere. If I am a new user, I open up my browser and I hit the system, how will be my experience? Okay, do I see the home page immediately or do I see it very late, okay? So it is not particularly good to take these times into the loaders, because if you have a loader that is hitting the server at 60,000 requests per second, okay, that loader is very busy, and it's not like a new browser that is doing absolutely nothing. So maybe the times that you get on the loaders are not really a good measurement of the experience that a new real-world user would have. However, we can mimic this in a probe machine that has very little load, still hits the server, but it will have an experience that would be similar to a new user opening the browser and hitting your system. One important thing that you need to configure from like the first moment would be the OS configuration. And in particular, there are three major things that we always bump into. The first one is the increase of the number of open files. This is really important because by default, for example, operative systems like Ubuntu or something, they come with a very small number, which is typically around 1,000. And if you are running a server that is, you know, that you want to measure, for example, can I sustain 100,000 connections to the server? Well, if you only have 1,000 open file, well, then the system at a certain point will say, hey, I cannot accept this connection because I'm running out of file descriptors, okay? So you need to configure this parameter. The second thing that we come into is on the client, and it's the number of ephemeral ports, because a client has to open, let's say, 60,000 connections, and if it opens 60,000 connections, it has to have 60,000 different client-side ports. But typically, operative systems have a much smaller range for these ports to be open, typically around 20,000. So it really depends on this case, how much load you want to start on your loaders, but this is a parameter that very often you trip, and then you get errors on the client, and it feels like, oh, why do I have this error? The server is not working fine. But the error is not on the server, the error is on the client. It cannot allocate a new ephemeral port to connect to the server. The other thing is the CPU governor. This is important because modern CPUs, they are really smart at tuning their frequency of load, of working. And so depending on the load on the system, depending on the heat that you have in the room, the power consumptions, and so on and so forth, there's a million rules that cannot be easily forecasted, especially when you try to apply something dynamic as the load on your system, right? Imagine a case where your loader starts at a very small load, but then increases over time. What can possibly happen is that when you have a small load, the CPU runs at a smaller frequency, but then you increase the load, CPU boosts up. On top of the operative system, you typically have the JVM. And so a couple of parameters that, or a couple of suggestions. I mean, some years ago, this would have been like 10 slides, okay? Because you had to tune a bazillion parameters on the JVM. Nowadays, thankfully, you use Java 21, and then you just go and you say, okay, I want to set the heap size, the maximum heap size with Java -XMX. And then I pick a garbage collector that does not, put any stick in my wheels. It's like, okay, I know that this garbage collector is super good, doesn't have long pauses, stop the work pauses to my application that can screw all my measurement times. And what I suggest is to use generational ZGC. Even though it is a concurrent collector and runs concurrently with your application, it's awesome. So if you have doubts, just use ZGC generational and all your GC problems will probably go away instantly. And if they don't, because you still have allocation stalls, for example, which is a typical problem of concurrent garbage collectors, you just increase the heap size and that will go away. And so you have just one tuning parameter, which is the maximum heap size. Super easy. The last parameter, the bug non-safe points, is a parameter that is useful for profiling, which will come in a few slides. So we'll talk about that a little bit later. So once you have tuned all your system, what is it that you have to do? Well, you have to create a load test scenario for what is it that you want to measure. So for example, it can be just, I want to measure the time my landing page renders on the browser, or how long does it take for the server to serve the 25 resources that are associated with the landing page. So not only the index.html, but also 4 JavaScripts or 4 CSS files, and then some other stuff pulled out from other sites, all the social links from, or small icons, etc., etc. What we suggest typically is to start very simple, and then know what scenario you want to test. Typical case that happened in one of our clients was, the scenario that is most important to us is the following. We land on the page, we click on the login link, we log in into the system. After the login, we go to the catalog, we browse the products of the catalog, we pick a product, and then we want to see the details of the product. That's a lot of steps that need to happen in order to test a scenario, right? You can do it, definitely, but what I'm suggesting here is start really small at the beginning, and then once you have your system that is working reliably, then you can make more complicated scenarios and test those as well. Regarding the tools to build these scenarios, there's a bunch of them, and all of them are, these days, pretty good, I would say. So they're kind of interchangeable, depends on the experience that you have with them, and so on and so forth. For the Jetty project, we use the Jetty load generator. That comes associated with another small project, which is the Jetty cluster orchestrator. So fundamentally, what we can do is that we can write a load test scenario that looks like a JUnit test case. We write the server-side code in a Java class. We write the client-side code on another Lambda, and then the orchestrator, fundamentally, what it does is says, okay, take this code, upload it to the server, and run it on the server. Take this code on the client, upload it to all the 4, 5, 6, 7, 8 generators that you have, and run them all. And then the orchestrator gives us a distributed log system so that we can say, okay, everybody ready? Go, right? And then we can start all the load generators at the same time together. Now, these features are typically available in other tools. For example, JMeter has agents that you can deploy on different machines and coordinate and etc. There are other tools like Work2 written in C, but Gatling is in Scala. There's native solutions on the cloud that cloud providers will give you to do load testing, like the Azure cloud or AWS provide this kind of things. Whatever is best for you, use that, but my recommendation is you have to know the tool that you're using, and we'll see in a little bit of details why is that the case. The last and most important things, once you have done your setup of the operating system, JVM, and you've written your scenario, the one thing that you have to do, and if you do not do the step, fundamentally you're just wasting time, is to enable resource tracking. You have to put this kind of monitoring in every piece that you're going to run. So that means the server, but it also means, most importantly, in all the loaders and in the probe. You want to know exactly who is the limit. In our experience, for example, especially with Jetty, the web server, the Jetty web server is crazy fast. There's no way so far that we've been able, with the machine and the hardware that we actually have, that we were able to put the server under stress at all. So what happens is that the clients, the loaders that we have, they go into stress way before the server. So we need 4 of them in order just to take the server at 15% CPU. And we need 4 loaders. I have no idea how many loaders we need to buy, so we do this on our own hardware, not on the cloud. And so we just said, okay, it's good enough. Jetty server is good enough that we buy 1 server machine, 4 loader machines, and 1 probe machine, and we have bought 6 machines, and that's enough. I mean, it's like, okay, we cannot push the server to the limit because we know that the client will go into limit way before. So it's really important to also resource tracking the clients. And you want to monitor CPU, you want to monitor network bandwidth consumption, you want to monitor SSD, you want to use perf on those machines to understand all the metrics related to CPU event counters. You want to use JHICCUPs to understand whether your system is undergoing through hiccups that can show up into the graphs and all the data gathering that you're doing in the response time, for examples. And so you can correlate, oh, there's been a long response time. Okay, let me go to the hiccups. Do I see at the same time a hiccup? Yes, okay. Well, then now I need to figure out the hiccup, but at least you know that it's not your application. You want to monitor threads, connection, and obviously you want to monitor response times. You want to monitor response types, meaning it's a 200 or it's 500. And then you want to monitor for errors. So this is the typical scenario. You have one server, you have a bunch of loader machines, all of them have resource tracking, and then possibly on the side you have a probe machine. Once you have prepared your setup, what you want to do is to establish a baseline. And what that means is that you actually run the load test. And you want to start small in order to be sure that everything works. And you want to be able to be reproducible, meaning you do a run, you get certain numbers out, then you do another run, and then what you want to see is you want to see the same numbers. Okay, if you don't, well, then there's something to investigate. Okay, and you want to record everything that you possibly can. Once you have a stable system, it's actually time to run the load test the way that you want to do in order to answer, remember, the questions that you ask yourself at the beginning. For example, the question could be, what is the load that will bring my server to 50% CPU, which is what you expect to run in production, okay? Or vice versa. You can say, I want to do a limit load testing. I want to push the server to the maximum. I want to see where is it that it breaks first. What is the resource that, stops working because it goes into saturation. And so what you need to do is just you run your load test and you gather all the data. You need to gather the data both on the server and on the client. Remember, this is really important, okay? And then you want to try to analyze the data that you get. And so in the previous presentation on eBPF, Brendan Gregg was mentioned, but I mention him again because this guy is just amazing. And so he came up with this methodology called the use method. Actually, the use method is an acronym for utilization, saturation, and errors. But actually, what you really want to do is that you want to analyze them in the reverse order. So you want to do errors first, then saturation, then utilization. Okay, we'll see an example about this. So errors, why? Because the first time that, for example, we set up our system to run the load test in Jetty, what was happening? It was happening that we had the DNS system in our thing resolving the wrong IP address. And so we just started the load test. Everything was super fast. It was like, whoa, what's going on? Well, it turned out that every single request went broke because it would say, oh, I cannot contact the server. I cannot even connect to the server. And so everything was super fast. But only when you look at the errors, you see, oh, none of the requests actually hit the server because they didn't even leave the client. Okay, so you really need to look at this. Another typical problem with errors is the following. On the client, you prepare all your load tests, but you make a typo in the URI that you're going to ask to the server. And so what you get is a million 404s on the client. And it turns out the 404s are really fast to be returned down to the client. And then you say, oh, okay, 1 second. I plan to do the landing page, the login, the browser, the catalog, and choosing a product, and it just returns like in, I don't know, 100 microseconds. That's really fast. But, that's not really the case because what you get out is just 404 on the first request, okay, because you have a wrong URI. So always look for errors first. Once you get rid of the errors, then you look at the saturation of your resources. And the saturation means your resource is at max capacity. And for example, that could be a network to, you have large responses that come back to the client. And at a certain point, if you have 60,000 responses per second, and each of them carries 1 megabyte of data, that's a lot of data to transfer over a network, right? And therefore, you cannot go to 120,000 requests per second or responses per second just because the network cannot make it, okay? So you really want to measure everything in order to understand what is my limiter, okay? Bear in mind that a resource may saturate even when the utilization is not 100%. Why is that? Because utilization of a resource is typically an average. And if you average over things, what can happen is that you can have a peak where you're saturating your resource, and then immediately afterwards, the saturation goes away, and maybe you don't use the resource that much anymore, okay? If you take an average of that, you say, well, okay, my resource is only, utilization is only at 50%. Well, but the problem is that you cannot push more because there is that one little moment where your resource usage goes 100%, and in that moment, you cannot push more, okay? Even if, in average, you're at 50%, you just can't push more, okay? And so we'll see an example about this also later. Once you get the numbers, so you're running your system, you're gathering all the data, now you have all the data, and now you gotta, look at the data and say, are the numbers good? You analyze with the use method from Brendan Gregg, and then you say, okay, are they good? Okay, and make sure they are consistently good over multiple runs, and then you can ask yourself the question, okay, can I improve these numbers? Like, for example, I went 50% with, 10,000 requests per second, 50% CPU, network is okay, no errors, all good. Okay. Can I do 20,000 requests per second, also, but staying at 50% CPU, right? That is a legitimate question because it will allow me to buy less machines on the cloud and be more efficient. So in order to answer this question, you need step 4, which is profiling. And the step 4 profiling, what is profiling? Profiling is fundamentally just a load test, typically run a steady state mode, where you add a profiler to your systems. All of them, again, clients and server. You want to monitor both of them, right? Typically, we recommend a profiler that use this particular system call, well, not system call, but JVM call, called async get calls trace. Because even if it is a non-standard call, that is the best way to get reliable data out of a JVM. So a sync profiler is a good profiler that does this, but JProfiler also can do that. We use a sync profiler in our experience with Jetty and with clients. A sync profiler is able to generate you something called flame graphs. So let me just, who knows what a flame graph is? Kind of valve for the audience. That's good. So basically, a flame graph is a way to, it's a graphical way to put all your data into a way that it's visually very easy to understand what is the critical path that is consuming the most of your resources, okay? And you can produce a flame graph for every resource type. If you want to have CPU flame graph, you know that, if you see like a special tower, what I call them, you know that that particular piece of code is the one that is consuming the most CPU. But you can do them for many other events, like allocations, you can do them for other things. And you run your load test with the profiling enabled, again, steady states, and then you analyze the things. And then it's an iterative process, right? So you run the load test, get the flame graph, look at the flame graph, and you see, haha, this is something wrong here. Okay, you change the code, because in the flame graph, you have the code path. Okay, so you see, haha, this code path needs to be fixed. Okay, you fix the code path, and you rerun the load test, you get a different flame graph, and then you say, haha, now this other part of code shows up, and so on and so forth. Like you rinse and repeat, and you just iterate over this in order to make your application more efficient. Okay, so enough with the theoretical talking here. Let's see some funny example of the war stories that we have that we've had with Jetty and other applications. So, example number one. This was a fun one to be honest. So what we wanted to do is that we had Jetty. We wanted to do a limit load test run, and we say, okay, can we push Jetty like to a real maximum? So we have 4 loaders. We started at 60K requests per second, and we slowly increased the loader rate, right? At a certain point, we arrived at 120K requests per second for each loader. And then we were seeing the CPUs here. Can you see the numbers over there? So you can see the last number, the green one, is the idle per CPU. So idle means it's not doing nothing. So every CPU was about 70% idle. Can you see the outlier though? There was one of them that was a 30% CPU idle. Okay, you can say, well, okay, that's a case, but it's okay. It still has plenty of stuff, to do. However, we look at the rate of the loader, and this is the graph of the loader. 120, this is the number here. Like, it should be a totally flat line where the loader sends 120,000 requests per second. This would be a totally flat line. But it goes up and down some days and goes down to 0 towards the end. It's like, what's going on? It's really weird because I just checked the math. Okay, so let's do the use method here. Okay, so were there errors? No errors. Okay, so let's see, no CPU saturation, obviously, because we just look at the average and it was 70% idle. Okay, so that means 30% usage only? Easy, plenty of space for CPU, no problem. There was no network saturation because the requests were really small, so the network was not a problem. All the parameters were nominal, and so why does it not work? So at this point, you have to apply a little bit of brain and know your system. How does it actually work? And so what was going on? It was the following, that the loader was using one thread to send the request. And so the way that it does this is send the request and then sleep a little bit, and then send the request and sleep a little bit, and loop around in order to achieve 60,000 requests per second. No problem. However, when you increase the rate, of course, the sleep time becomes less and less and less and less until maybe there is a moment where you send the request, you come back, you're supposed to sleep, but you figure out, oh, no, I'm already late. I have to loop around and send another request because otherwise I cannot keep up with the 120,000 requests per second. So what was going on is that one thread was spinning around like crazy. From time to time, that thread was sleeping, and the operative system was saying, oh, you're sleeping? No problem. I'm taking you off this CPU, and then when you wake up, I'm going to schedule you on a different CPU. So if we look at the CPU usages, every CPU was actually working a little bit, but this thread was jumping around every CPU, but the thread was the one that was looping around like crazy, and it could not push more than 120 requests per second, so much so that the graph was, all up and down and spiky. Well, we used a tool called TTOP, thread top, at this URI, and turns out that tool could actually tell us, hey, this thread, look at load generator, blah, 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 sender -0, is actually at 98.43% usage. Okay, so it was saturating. Solution for this particular case, well, in our tool that we use for that, we can specify on the tool, hey, you use 2 threads for sending requests, not just one, and that will solve the problem. Okay, so that's what I mean by you have to know your tools. You just cannot blindly go there and say, oh, I'm going to use, AB or Work2 or, Gatling, and just, do a quick review of the documentation, hit a bunch of parameter and command lines, enter, no monitoring, no tracking. I have no idea what happens on my client system, and I just blindly trust the tool to do the work for me. It actually doesn't particularly work well in this case. Okay, so you gotta know what you're doing and how the client works. So example number 2, This is also a super fun one. Took us 1 week to figure it out. So in Jetty, we have two threading. Jetty has a quite sophisticated threading system. And you can configure the threading model in Jetty to run in different modes. One of the modes is what is typically known as the event loop mode, or selector thread mode, where fundamentally you have a network event, and then the thread that picks up that network event is also the one that does the reading from the network, the parsing of the HTTP request, the calling of the application, the producing of the response, and then goes all the way back into the network, and then picks up another socket that might be waiting there to be read, parse, call the application, send the response, and so on and so forth, right? This is one model. The other model that Jetty can use, which is the default model that Jetty uses, is we have a network event, we pick up a socket, and then we pack it into a runnable, and then we give the runnable to a different thread, okay? And then that thread does the reading, the parsing, etc. This means that the selector thread can go immediately back and look at the second socket, okay? Pack the second socket into a runnable and give it to another thread. So now there are 3 threads fundamentally going around, right? One is the selector thread, and then we have 2 additional worker threads for each socket. And okay, so we said, we have no idea, but let's run a load test in the 2 different modes, and let's see what we get. It was just curiosity. We had no expectation. We didn't know which one was faster, although we had some idea. Because obviously, if you dispatch to different threads, well, then you have a little bit of a cost into context switching, and then you're obviously using 3 threads instead of 1, so you expect to use more resources, right? So we ran the test, and we discovered that one of the 2 configuration runs twice as fast, or one of the 2 was twice as slow. And that was a big surprise, because you say, wow, that's a big difference for just changing a single parameter in the threading model. And then it was also not the configuration that we expected to be that slow. I mean, it was actually the selector thread mode. The event loop configuration was twice as slow, right? But then we kind of went into applying a little bit more, and these are the graphs, right? So this is a graph report of the processing times taken at the server side. Every bar is 1 second, and it is basically the bottom of the bar is very close to the x-axis, but it's measuring the minimum response time, the processing time that we had at the server, and then the top of the bar is the maximum response time that we had in that 1 second, okay? And in that 1 second, we had 240,000 requests for every second, because that was the load that we imposed on the server. And the bar you don't see the scale, but fundamentally the bars go from about 5 microseconds for one response to here about 3 milliseconds it's the top of the bars are 3 milliseconds. And you can obviously see that the ones the graph below, which was the event loop one, is worse, right? It's the same scale, so it has to be much worse. Okay, so we apply some brain to it and say, okay, wait a second. The moment we start measuring the time is when we start parsing the request. And it doesn't matter what happens before, whether we dispatch a thread or we don't dispatch a thread, or we wait, we do one full request and then we come to the second request. It doesn't really matter, because even imagine for the second socket, right? We do all the work for the first socket, but when we come to the second socket, there's a moment where we start taking the time, and that time is irrelevant with respect to how long did it take for the first socket to do any processing, right? And so we said, wait a second, so it doesn't really figure, because the processing times should be exactly identical, because I'm measuring from here to there, and that code that runs in between the 2 moments is exactly the same, and it's always run by a single thread. It doesn't matter if it's a selector thread or a worker thread, okay? However, it was the same code that was running twice as slow. How is that possible? Any guess? Well, we didn't guess, we measured. We applied perfstat, and look at that. The perfstat reports was, oh, the CPU frequency of the CPUs was throttled down in one case. And so in one case, one CPU was working at 2.6 gigahertz, and the other case it was working 1.3. Why was that? Well, the reason for that was that the configuration for the selector loop, we had a machine with 32 cores. And the configuration for the selector loop was saying, oh, we only want to have 24 selector threads because we think it's enough. And so whatever mechanism inside the CPU is saying, hey, wait a second, I have 32 cores here, but 8 of them, you don't even use them. And so why should I spend more time in giving you more processing power if you don't even use 8 of my cores? Okay, so I'm gonna keep you at 1.6 gigahertz, thank you, bye. And so until you actually turn on perfstat, you cannot figure this out. It's like, okay, I'm running my load test, shitty results, my application is slow, crappy coders, I'm gonna fire all the developers until you figure out, oh shit, that was not the problem. The problem is that I forgot, remember what I said to you in a previous slide, that you have to set your CPU governor to performance, because that is what locks the CPU frequency of your CPUs that is variable into a fixed value, whatever that is for the CPU you're using, and that will guarantee to you that the results that you're getting will be consistent, okay? Okay, long story short for this one, we went back into the tuning the CPU governor, and everything went back to normal. The 2 times were back to be the same. Example 3, we were looking for optimization. So look at, this is a flame graph, okay? The important thing, don't read the small things, but imagine this is a stack trace. In the vertical side, you have stack traces, and each line is a frame, it's a stack frame. You can see these 2 towers on the left, right? Those 2 towers are the allocation of an I/O exception in different code paths. Unfortunately, those code paths were in the hot path for serving a request in the Jetty engine, okay? And so easy, 10% of the time spent for an I/O exception that we don't throw and we just use for internal stuff. Not good. And so what we have done is that we look at the code, we have the exact stack trace, so we just go to that particular piece of code, super easy, we remove the allocation of the I/O exception. You can see that now the 2 towers on the left are gone. These are the 2 flame graphs compared to one another. You can totally see that fundamentally the tower in the middle, the small tower in the middle is now this tower here, slightly enlarged, because this is a percentage thing, it's 100%. So because the other 2 are now absent, every other tower is a little bit wider because it is a percentage representation, right? So very easy to fix performance issues with flame graphs. Example 4 is an interesting one because there was a certain moment in the development of Jetty 12, our latest release, where we had to take an API design decision, okay? And we had 2 choices. The first choice was, how do we handle a request? How do we provide to users an API to handle the request? And this was the first attempt. Well, first attempt, we kept this API for months and months and months. So we said, okay, we give the users a request, the handler tells me whether it is able to handle that request or not. For example, is the request for that particular handler? And it says, returns null if it is not for that handler, maybe for a different handler. Or it returns a processor if it is handling the request. And then the processor will get in the request, the response, and the callback. And this split of the API was very nice because it was very clean. It was saying, until you tell me that you can handle the request, I will not give you the response, which is mutable, okay? I will only give you a read-only request, which you can inspect, figure out if this request is for you, and if it is for you, give me back a processor, okay? Very clean API. But at a certain point, Greg Wilkins, which is the founder of the Jetty project, came up with this idea and say, hey, can we try this instead? We just have a single API. We give all the things into one spot with the contract that you cannot touch the response object unless you return true from Boolean handle, okay? Meaning, I want to handle this response, this request and response, right? But if you don't and you return false, don't you dare taking the request object, modifying the request object, okay? So it's less clean API, but way simpler. How about the performance? Again, the graphs that we gathered, it's not particularly clear, but you can see the number that with the processor, the numbers were worse. So like Greg Wilkins says all the times, Jetty is not just a web server. We want to be a fast web server. And so we eventually settled on the second solution, even if from the point of view of the API, it was slightly less pure, let's say, but it was way more performant. So conclusions. Performance analysis can be hard, but it's possible. It's 2024, there are the tools available to do whatever you need to do. There's plenty of tools available from loaders, profilers, flame graphs, and resource usage tool, whatever. Remember the 4 steps: set up and configure your systems, run a baseline and be consistent in reproducing the numbers, do your runs and gather and try to get the answers for the problem that you want to solve, the one problem that you want to solve, and then if you need, go into profiling in order to improve your numbers. Analyze everything with the use method, and remember it's the other way around, and then apply your brain, because sometimes it's not evident, okay, and you need to really try to figure out what is the problem. Thank you.